Thank you. Good afternoon, everyone. I'm Arnab Sarkar, and I'm a PhD student at the Institute of Astronomy at the University of Cambridge. Today, I'm going to talk about a unified model for the evolution of CVs and AMCV and stars. So let me begin by explaining what CVs are. So cataclysmic variables are a class of interacting binaries, wherein a low mass secondary star loses mass to a white dwarf in the form of an accretion disk, and AMCVNs are a subclass of CVs wherein the donor is usually hydrogen deficient or evolved. So the spectra of these systems usually do not have hydrogen, and they are usually observed with shorter orbital period of around 60 minutes. From now on, I'll call the primary or the accretor as M1 or MWD and the donor as M2. So how do CVs evolve? So initially they start as detached systems. Loss of angular momentum brings them close together until the donor star overfills its Roche-low. And at this point, it becomes a mass transferring CV. And at this point, we call it a CV. Before this, the system is detached and we don't call it a CV. So if we plot a histogram of the observed orbital periods of a CV, of all the CVs, we will see two prominent features. Number one is a dearth of mass transferring CVs between 2 to 3 hours, which we call the period gap. And we see a peak in the observed period of between 80 to 86 minutes, which we call the period minimum spike. The evolution of CV is driven by the loss of angular momentum from the system, which is due to two mechanisms. Number one is due to angular momentum loss by gravitational waves, the mechanism of which is known, but the angular momentum loss due to magnetic braking, which is the second mechanism, the formula of it is not known, and we are only currently working with empirical formula. The other thing that governs the evolution of CVs is the interplay between the mass loss timescale and the thermal timescale, wherein if the mass loss timescale is greater than the thermal timescale, the orbit shrinks, and when mass loss timescale becomes comparable to the thermal timescale, the orbit expands as a result of mass loss. Therefore, we get a period minimum when the system evolves from a shrinking orbit to an expanding orbit, and that's why we get this period minimum. And our aim is to model the evolution of CVs with a physically motivated angular momentum loss mechanism, which we do by using an alpha omega dynamo mechanism in the donor star. Let me now explain what an alpha omega dynamo is quickly. So an alpha omega dynamo is the mechanism with which a differentially rotating star can maintain long-term magnetic fields. So how this works is due to two effects. So if you have poloidal field lines like here, differential rotation leads to twisting of these poloidal field lines to form toroidal field lines, and this is called the alpha effect. Whereas due to anisotropic turbulence, toroidal field lines twist to form magnetic loops, which give rise to poloidal field lines, and this is called the alpha effect, and the former is called the omega effect. So with these two, you can have self-sustaining magnetic fields, and we come up with something called the double dynamo model, wherein there are two such alpha omega dynamos in the donor, one in the convective envelope and the other at the boundary between the radiative core and the convective envelope. So since these donors are low mass stars, you have a convective envelope and a radiative core. So these two dynamos lead to magnetic winds which carry away angular momentum and thus cause magnetic braking. And the boundary layer dynamo ceases to operate when the donor becomes fully convective. And this leads to the donor system going out of thermal equilibrium, and the donor shrinks back into its Roche-low and causes the mass transfer to stop. And at this point, we are at the top of the period gap. Then mass transfer commences again when gravitational radiation plus some contribution due to the convective dynamo causes the donor to again fill its Roche-low, and then the system evolves further. However, we do all that under some assumptions. We assume that there is tidal locking between the convective layer and the orbit, so that the angular velocity of the orbit is equal to the spin angular velocity. We also assume that the radiative core is not spinning at all, and it's not linked to the convective envelope. We assume that the breaking happens only due to the colloidal component of the magnetic field. And finally, we assume that mass transfer is fully non-conservative, such that whatever mass the white dwarf accretes is removed in the form of nova eruptions. So let me explain how the system evolves in the orbital period donor mass plane. So we start with a 1 solar mass donor and a 1 solar mass white dwarf with 12-hour orbital period, and let the system evolve with the DD model. So the system evolves from right to left, where first the orbit just shrinks, and till this point where Roche lobe overflow begins for the first time. And then mass loss happens and the system evolves from right to left until this point where the boundary layer dynamo stops operating since the star becomes fully convective. And then the system gets detached and it's not a CD anymore till it drops to this point, which is the lower end of the period gap. And then GR plus convective dynamo lead to Roche lobe overflow again. And the system evolves like this till the mass loss timescale and thermal timescale become comparable and the system expands, thus the period minimum. The other feature that I talked about was a period minimum spike, and there has been discrepancy between the theoretical and observed period minimum, wherein theoretical estimates give 65 minutes as the period orbital period minimum, whereas observations predict it to be around 80 minutes. So we attribute this to an extra angular momentum loss mechanism below the period gap due to the fact that complete cessation of magnetic field in fully convective stars is not plausible, and there has been evidence of some remnant magnetic field in fully convective stars. So we use this fact and we come up with an extra angular momentum loss below the period gap. How we model this is by enhancing the convective dynamo by this proportionality constant, which is quite ad hoc, but we multiply our angular momentum loss due to the convective dynamo by m conv over m raised to power alpha, where m conv is the mass at which the star becomes fully convective, which is around 0.2 to 0.3. And by changing alpha, we can get where we have our period minimum. So you see that for 3 alphas, you have 3 different period orbital period minima, and we can tweak it to get what we want. So I think for 4.6, we get around 82 minutes. And the other thing we also need to consider is how the trajectories depend on the accretor mass. So what we have here is the same trajectory, but for 3 different accretor masses. So we see that for smaller accretor mass, the system goes more out of thermal equilibrium simply because smaller accretors lead to faster mass transfer. So they go more out of thermal equilibrium and the period gap is bigger. And more massive accretors lead to smaller mass transfer rate and the system is less out of thermal equilibrium and thus smaller period gap. So we also need to take this into account. How we do this is by making some sort of a probability distribution. We divide the orbital period parameter space into small bins, and to each bin we assign a weight based on the amount of time a particular trajectory spends in this orbital period bin. So here we have, then we get this histogram. So here in this plot we have what I described right now for all our white dwarf masses. Let me explain the orange curve, which is for an accretor of 0.7 solar mass. So we see that the system spends most of the time between 4 to 5 hours, but nothing between 2 to like 3.8 hours. And then it spends some time here as well. So we assign some weights to these and we get trajectories that just depend on the white dwarf mass. In order to get one single distribution from out of all these, what we do is we just scale them. scale the previous plot to take into account white dwarf mass distribution. So we scale them based on what the how frequently these accretors exist in observed systems. So the most number of observed CVs have white dwarf mass of 0.83, which decreases for heavier masses, and also this frequency decreases for smaller masses. So by assigning another weight to it, we get a scale distribution. If we look at this distribution, we see that these dotted lines, which represent the period minimum spike, they match these dotted lines represent the observed period minimum spike, which matches very well with our peak here. We also see this is the lower and upper end of the period gap, and we also get good match with observations here as well. Finally, we compare our results to observations. So these are all our trajectories for different white dwarf masses, and we compare these to some of the observed systems with good observed parameters. Below the period gap and right above the period gap, we have very good matches, and we do not get very good match for these systems, and we believe that these systems are systems where the donor is a bit evolved, so they do not exactly follow the canonical CV trajectory. So we have matched them with AM-CVN trajectories, and we have gotten good match as well. I would like to conclude by saying that our DD model produces the period gap and the period minimum spike in the CV distribution quite well. As a consequence of the DD model, we see that angular momentum is lost from the system much faster above the period gap, or in other words, the time scale for mass loss or magnetic braking is shorter for the DD model compared to, let's say, Rappaport's empirical model or Nigi's empirical model, which is like Rappaport's model multiplied by an ad hoc factor. So we see that our DD model causes the system to lose angular momentum much faster, and this has profound consequences, as can be seen in this plot. So here we plot a system with one solar mass white dwarf and one solar mass donor with an initial period of 2.3 days under these three mechanisms of angular momentum loss. We see that for the same initial parameters, the DD model still gives a canonical CV with the period gap and the period minimum at around 80 minutes, whereas Nigi's model or Rappaport's model gives rise to AM-CVNs, where the orbital period minimum is smaller than 80 minutes, and there is no period gap anymore. So this means that DD model drives this evolution on a much smaller time scale. Thus, more systems can become canonical CVs. So that would mean that more systems can also form AM-CVNs. So this is what we have explored in our upcoming paper, but I do not have time to explain this further. But if you have questions, I'll take them. Finally, I would like to conclude by saying what we can do in the future with the DD model. First, we can analyze unusual CVs or AM-CVN candidates, which will further strengthen or weaken our claims of the DD model. We can also look at magnetic braking in AM-Her stars. AM-Her stars are CVs where the white dwarf has a magnetic field. A very strong magnetic field can actually amend the magnetic braking of canonical CVs, and we can also model that. And finally, we can also look at how the DD model would spin down some low mass stars. So we are also working on this, and I hope we get good results with this. That's all for now. Thank you for attention. I'll take any questions.
Questions?
Thanks. I was just wondering, so you have these two dynamos, and I guess each one is driving some magnetic braking, but how do you decide what the relative weighting is? And
yeah, so the boundary layer dynamo is mostly due to differential rotation between the core and the envelope. So what happens is if the envelope is spinning at the same angular velocity as the orbital period and the radiative core is not spinning at all, the rate of differential rotation is of the order of omega odd. So this dependence makes boundary layer dynamo much more dominant compared to convective dynamo, which only arises due to small changes in the convective envelope. So for most of the evolution till the system becomes fully convective, it's mostly dominated by the boundary layer dynamo, and the dominance comes as a result of this assumption.
Okay, thanks.
Cheers.
More questions? Ken?
Can you go back to your previous slide?
Yeah.
Thanks. So I must be misunderstanding something. So in the top left plot, so let's say at so at a given mass, so let's say 0.5 solar masses, doesn't that fix an orbital period? Shouldn't all the orbital periods be the same? I must be misunderstanding the plot.
So you're saying that if we take, let's say, 0.4 solar mass, all their orbital periods should be the same?
Yeah.
Right,
isn't it just a function of the average density of the donor?
Well, not quite, because if you have a stronger angular momentum loss, if the system is more evolved, it goes more out of thermal equilibrium. It behaves differently than a system which is just composed of hydrogen. So I would say that because the donor is evolved or the composition has changed, the mass transfer rate is a bit high. That's what I have seen. And owing to the higher mass transfer rate, the system goes more out of thermal equilibrium and it gets more bloated. As a result, the orbital period is also high for a given mass.
Okay, but to get a difference of that orbital period, like the difference in orbital periods at given mass, it's really big. So
yes, that is because the DD model's angular momentum loss rate is about 10 times as fast as the empirical formula. So it leads to quite profound differences in the results. Yeah, that's what is intriguing.
Okay, thanks.
Hi, this is Jim Fuller. So following up on that, so you have faster angular momentum loss. So that means you'd predict larger mass transfer rates above the period gap. Is that right?
Yes.
So have you compared that with what Anna talked about earlier? It sounds like the observations often indicate that you need lower, observations are often lower mass transfer rates than what the RVJ model predicts. If I understand correctly.
Sorry, I did not attend the first lecture, but what you're saying is you should have lower mass transfer rates. That's what observations suggest?
I believe so.
I see. Yeah, that's quite interesting because this model predicts it in quite the opposite. But there are a few dwarf novae and few unusual CVs that I have just looked at very briefly, and they lie quite away from the canonical trajectories that the RVJ or KBP model would predict. But with the DD model, I see some good match. So I'm not sure. Maybe I need to look at it.
Okay. I have one comment more. If you increase the evolutionary timescale above the gap, the anti-evolution is faster, and you produce even more period bounces, which might be a problem.
Sorry, can you?
No, we have this big problem that we don't find enough period bounces when they turn around. There are predictably many from population synthesis. If you accelerate the evolution, stronger magnetic braking, then you predict even more if you put this into population synthesis. So I mean,
Right.
doesn't mean it's necessarily wrong, because all the other models also disagree with the period boundary, but it would make the problem even worse.
Well, yes. Right. So the evolutionary timescale does increase as we move closer to the period minimum.
Yes, of course, but the total time decreases. Yeah.
Yeah.
Okay.
That I haven't looked at.
I also have a question, but maybe we have to continue.
Right.
So thank you very much.